You know, we've all had them. A little scrape, a cut, and then that scab shows up. It seems so simple, right? Almost kind of boring. But what if I told you that little patch of dried blood is actually the rooftop of a massive microscopic construction project? A biological masterpiece that is just breathtakingly complex. Okay, let's get into this.
Right, so that tiny little breach in your skin, it doesn't just trigger a simple patch-up job. No way. It kicks off this perfectly choreographed biological cascade, a series of events that have been fine-tuned over millions of years of evolution. It all happens automatically, but today, we're going to pull back the curtain and see exactly how your body builds itself back together.
So at its core, what is wound healing? Well, it's the body's fundamental blueprint for repair. And I love this definition because it really gets to the heart of it. It's not just about plugging a hole. It's a symphony, you know? You have all these different players, all these different cells arriving at the absolute perfect time to do their very specific job, all to create one seamless repair. And our symphony begins with a code red emergency. The first act is all about pure, unadulterated damage control. The second your skin is broken, two things have to happen, and they have to happen with incredible speed. You gotta stop the bleeding, and you have to block any invaders from getting inside. This first phase is called hemostasis, and it happens in moments. When a blood vessel is injured, it exposes this protein called collagen, which acts like a blaring alarm bell. Instantly, hundreds of thousands of tiny cells called platelets swarm the area, sticking to that collagen and forming a quick, temporary plug. But that's not strong enough. So, this chemical chain reaction, like a line of falling dominoes, kicks off. And the end result? The creation of these really tough fibrin strands that weave a durable mesh, trapping blood cells and sealing that wound for good. That, right there, is your clot. So, the bleeding stopped. The leak is plugged. But the site is a mess. It's full of cellular debris and, more importantly, potential bacteria. So, what does the body do? It calls in its specialized cleanup crew. This is the critical inflammation phase, which you've definitely experienced as the redness, the swelling, and the warmth around a fresh cut. That's not a bad sign. It's a sign that the cleanup is well underway. And here are the stars of that crew. First on the scene are the neutrophils. These are your frontline soldiers. They show up within a day, and their entire job is just to hunt down and devour any bacteria to prevent an infection. Then, about a day or two later, the macrophages arrive. You can think of them as the site foremen. They finish up the cleaning, but, and this is so important, they also release powerful growth factors. These are chemical signals that basically shout, all right, the site is secure, time to rebuild. And that signal kicks off our next major phase, proliferation. This is the official construction phase. This is where the body starts laying down the foundation for brand new tissue, right there inside the wound. And the key structure that's built during this time is called granulation tissue. You've probably seen this. If you've ever kind of peeked at a healing wound and saw that bumpy, beefy red tissue inside, yep, that's it. That's the brand new, fragile scaffolding that's filling the gap. So what is this new tissue actually made of? It really has three core components. First, you've got fibroblasts. Think of these as cellular weavers, and they are frantically producing a new collagen matrix. Second, to power all this work, new blood vessels have to sprout in a process called angiogenesis, and they deliver all the vital oxygen and nutrients. And third, the material itself is type 3 collagen. Just think of it as the quick and dirty, weaker scaffolding that gets the job done fast. But you know, the body isn't satisfied with just a temporary patch. The final and longest phase is all about remodeling. This is where that quick fix is meticulously transformed into a durable, long-lasting scar. And the most critical step of this whole process is what I like to call the great collagen switch. Specialized enzymes come in, and they systematically break down that weak, disorganized type 3 collagen, and they replace it with type 1 collagen, which is a much, much stronger, more organized version that provides real, lasting structural integrity. Now, at the same time, something incredible is happening. Some of those fibroblast cells, the weavers, they transform into this kind of hybrid cell called a myofibroblast. And what's so unique about them is that they actually contain muscle fibers. They literally grab the edges of the wound and contract, physically pulling it closed and shrinking the final scar. It's amazing. But after all of this incredible work, the clotting, the cleaning, the rebuilding, the remodeling, here's the catch. The final scar tissue never ever actually regains the full strength of your original uninjured skin. It maxes out at about 70 to 80% of its initial strength. It's a permanent, slightly weaker reminder of the repair. This whole symphony is beautiful, but it's also incredibly delicate. If just one of those instruments is out of tune, the entire process can just fall apart. So let's take a look at what happens when this amazing process goes wrong. A diabetic foot ulcer is a really tragic and honestly perfect example of this. The high blood sugar impairs those neutrophil cleanup crews, which leads to constant infections. Then, poor circulation, a condition called ischemia. It just means not enough blood flow is getting there. This starves the site of oxygen, so the whole rebuilding phase just stalls out. In essence, nearly every single phase of healing is sabotaged by the underlying disease.
But what happens when the opposite occurs? What if the repair process is just too aggressive? What if the construction crew never gets the signal to clock out and go home?
Well, this leads to what's known as pathological scarring. Now, a hypertrophic scar is raised tissue, sure, but it respects the original boundaries of the injury. It stays within the lines. A keloid, on the other hand, that's a scar that grows completely uncontrollably, spilling far beyond the borders of the initial wound, almost like an invading army.
And the reason is cellular. In people who have a genetic predisposition to this, those fibroblast cells we met earlier become hyperactive. They literally never receive the biological off switch, so they just keep producing massive amounts of disorganized collagen, creating what is essentially a benign tumor made entirely of scar tissue.
You know, when you take a step back and you look at the entire process, from that first little platelet to the final scar, it's truly remarkable. This quote says it all. It's a beautifully conserved evolutionary mechanism. From the smallest paper cut to major surgery, our very survival has always depended on this ancient, innate ability to rebuild. And that leads to a final, really fascinating question. We now understand this natural blueprint better than we ever have before. So what happens when we move beyond just helping this process along and we start actively engineering it with things like regenerative medicine? That's definitely something to think about the next time you see a simple little scab forming.